All right, so now that we know how to put all of those things into our calculator and do all of those matrix operations in our calculator, now we want to look at some applications of matrices and determinants in section 8.5. So at this stage, I would not be assessing, do you know how to find the determinant of a 3 by 3? I would be assessing, do you know how to apply it to things like we're going to look at today, like area of a triangle and collinearity of points and that type of thing. So you would be doing the actual matrix and determinant work in your calculator. It's the application that we're interested in. So the first thing they tell us here in 599 in section 8.5 is how to find the area of a triangle if you only know 3 vertices. Okay, think about this for just a second. At this point right now, if I only knew my 3 vertices, that was all that I had, just 3 vertices, how would I have to find the area of that triangle? I'd have to use distance formula for all 3 sides, so that's 3 distance formulas right there. Then what? I could do 1/2 base times height if I knew the altitude of the triangle. To find the altitude of the triangle, though, I'd have to like create a right angle and then solve, and that doesn't sound like a whole lot of fun. We do have a formula, an area formula for a side. Do you remember that? Yes, Heron's area formula. The square root of s times s minus a times s minus b times s minus c. Okay, but still, that's 3 distance formulas and then an area formula. So that's like 4 problems in one just to find the area. There's got to be a better way to do that. And so that's what our matrices and determinants are going to enable us to do. They tell me that if I want to find the area and all I know are the 3 vertices of the triangle, put the first vertex, that point right here, followed by a 1. Put the second point in the second row followed by a 1. And then the third ordered pair in the third row, followed by a 1. Then multiply it by either a positive or negative 1/2. Is area negative? No, not until you get to calculus anyway. So for right now, we're going to multiply by either a positive or a negative, whatever it takes to make my area positive. We're not going to put plus or minus on our answer, okay? So let's go through, for example, number 1. Our first row here, we're going to take 1, 0, the ordered pair, x1, y1, and then follow it by a 1. All right, what would our second row for that be? 2, 2, 1, and then what about our third row? 4, 3, 1, perfect. Now, this is the determinant that we put in our calculator that I mentioned to you. Hey, we're going to use this for example 1. We threw it in our calculator. This was matrix C that we took the determinant of, and we got -3 just a moment ago on our calculator. So, if we do 1/2 of 3, that's going to give us 3 halves, or 1.5, and then we would want to multiply by the negative out of the plus or minus so that negative times negative would give us a positive 3 halves. So again, we're not going to put plus or minus in front of that. We're going to use either the positive or the negative, whatever we need to, in order to get a positive area. All right, do you remember from your geometry toolbox what collinear means? Collinear. Do you see any root words in there that might help? Linear or line,
Co meaning 2.
Co meaning 2 or more, You're all around it, so close. It's if you have if you're talking about something being collinear, you're talking about points that are on a line. So if we want to figure out if 3 points are collinear, if 3 points are on a line, how much area would 3 points that are on a line, how much area would they encompass? 0. If they're 3 points that are straight in a line, they're not going to encompass any area, right? So if they're collinear, their area would be 0. If they're not in a straight line, even if they're just slightly off, but if they're not in a straight line, like these two are collinear, but this one's not, then you're going to encompass some area. So let's take that same area formula we had just a second ago and apply it here. Because we could say these 3 points are going to be collinear if their area is 0. If their area is not 0, then they're not collinear. They forgot part of the area formula right here. There's supposed to be a plus or minus 1/2 out in front. What's half of 0? What's half of not 0? Still not 0, right? So the 1/2 is irrelevant. They're just trying to save you a little bit of work and a little bit of time. So that's why they didn't put the plus or minus 1/2 out there. Okay? So example 2, they give me 3 points, -2, -2, 1, 1, and 7, 5, and they ask me, are these collinear? All right? So let's go through and let's set up the determinant here. What's my first row going to be? Second row?
1, 1, 1.
And third row?
7, 5, 1.
Perfect. All right, so I would throw that into my calculator to get the determinant, and the determinant I get is -6. Are those 3 points collinear? No. And again, you can see it doesn't matter if I had multiplied that by 1/2, I would have gotten 3, and negative would have made it +3. That's still not 0. So the question is simply, when they ask me, are they collinear, you could simplify it down to, is the determinant 0? All right, example 3, we're going to use matrices and determinants to solve systems of equations using something called Cramer's rule. Now, you did Cramer's rule in Algebra 2, so you've seen this before. But in Cramer's rule, we take the system of equations and we create first the coefficient matrix. Now, remember, the coefficient matrix is when you just pull out the coefficients, 4, -2, 3, -5. That would be my coefficient matrix. I'm going to call that D. All right? Then I'm going to replace, for D sub x, I'm going to replace the coefficients of x. So the coefficients of x were 4 and 3. I'm going to replace the coefficients of x in the determinant with the only other numbers that I had, and that was my constants, 10 and 11. And again, I'm going to call that D sub x. Then I'm going to have a determinant D sub y, and in D sub y, I'm going to replace the coefficients of y, -2 and -5, with the only other values that we have, and that was the constants, 10 and 11. So we're going to call that D sub y. Now, those are little 2x2 determinants. So let's go through and evaluate them. So that would be -20 minus a -6, so -14. And then -50 minus a -22, so -28. And then 44 minus 30, so 14. X will be equal to D sub x divided by D, and y will be equal to D sub y divided by D. So if I come over here, D sub x was -28 and D was -14. So -28 over -14 would give me 2. And D sub y was 14 and D was -14. So 14 over -14 would give me -1. And that would be the solution to that system, to -1. Now, there's not anything algebraically true about this. It's just a little mnemonic device to help me remember the formulas. But if you'll notice, if I divide these d's right here, I would just be left with x. So that's an easy way to remind me, d sub x over d, d sub y over d. If I'm going to solve a system of 2 equations with 2 unknowns, personally, am I going to do it that way? No, I'm probably going to use elimination. But I also can use Cramer's rule to help me with a system of 3 equations with 3 unknowns. And up to this point, we don't really have a good way to do that. We have several ways to do that, just none of them are fast or easy. So let's apply Cramer's rule to this 3x3. All right, I'm going to start the same way, where I'm going to pull the coefficient matrix and call that D. I'm going to replace, for D sub x, I'm going to replace the coefficients of x with the only other numbers that I have, and that was the constants, 1, 0, and 2. For D sub y, I'll replace the coefficients of y with the constants. And so to kind of continue that same pattern for D sub z, I'll replace the coefficients of z with the only other numbers I have with the constants. Now, I am not going to work 4 3x3s. I mean, that would be crazy to do 4 3x3 determinants. That would not make this an easier method from the other ways that we know to do this. So we're going to throw these determinants into our calculator and let it do them for us. So when my calculator does these 4 determinants for me in less than a second, then this becomes a much more feasible method, because x is still d sub x over d, y is still d sub y over d, and if we continue that same pattern on for z, z would be d sub z over d. So let's go grab these values that we got from our calculator. D sub x would be 8 and d would be 10. So 8 over 10 would give us 4/5. D sub y was negative 15 and d was 10. So negative 15 over 10 would give us negative 3/2 for y. And then d sub z was negative 16 and d was 10. So negative 16 over 10 would give us negative 8/5. And that would be the solution to our system. So if I'm going to ask you to use Cramer's rule for a 3x3, I'm either going to have to get you just to set it up, or you're going to have to use your calculator to do it, because 4 3x3s is just not time effective. Okay, so if I'm going to let you use your calculator to solve a system of 3 equations with 3 unknowns, there is a much better way to do that. If I didn't have my calculator, I probably wouldn't be doing it by Cramer's rule anyway, because I'd have to do 4 3x3s. If I have my calculator, then I have a fast, easy way to do reduced row echelon form, right? So maybe they tell me, you know, set it up by Cramer's rule and then solve. Okay, I could set it up by Cramer's rule. I could still solve by reduced row echelon form. When you get to a system of 3 equations with 3 unknowns on the test, it says solve this by any method that you want to, including throwing it in your calculator. So look how fast and easy. We are finally to the point we looked at probably 4 or 5 different ways of solving a system of 3 equations with 3 unknowns. Look at the fastest, easiest, best way to do this. Take your system of equations and write it as an augmented matrix. So I'm going to go through and pull out the coefficients. Negative 1, 2, negative 3, 1. Negative 1, 2, negative 3, 1. 2, 0, 1, 0. 2, 0, 1, 0. 3, negative 4, 4, 2. 3, negative 4, 4, 2. That is the matrix that we put into our calculator for E. And if you'll remember, with just a few pushes of the buttons on our calculator, we were able to get reduced row echelon form, whether you wanted it in the decimal form or in the fraction form. You are staring at your answer right here. 1x is equal to 4/5. 1y is equal to negative 3/2. 1z is equal to negative 8/5. That is that same solution that we got right there. That is a practical way to solve a system of 3 equations with 3 unknowns. Put the augmented matrix in, hit reduced row echelon form, and then you've got your solution either in fraction or decimal, whichever you prefer. Okay, so here is our homework for tonight. You are using your calculator tonight to do every single one of these. I want you to do them on your calculator so that you can practice them, with the exception of your challenge, because we're still practicing putting something in row echelon form. And then we have our quiz tomorrow over 8.3 to 8.5. Non-graphing calculator only. We are still doing these by hand on our quiz tomorrow and not doing them on the calculator. Because you're not going to have your graphing calculator, then I will not ask you to find the inverse of a 3x3 or the determinant of a 4x4, since you won't have your graphing calculator. So that's 2 things you won't have to worry about for the quiz tomorrow. Okay?